This was the ID. Bunch of people and stuff like 5 times. Couple of them will go up the review is a nice blue spark. Brave few.
Yeah. We got one more person here already than we did last week. Yeah.
I had other stuff, that's why I had to join. I don't know if we find that sad or impressive. I know one thing, it's not gonna be fun walking back. That's
Yeah.
I'm more excited to drive across town.
Slide on a few places.
literature review.
What?
Anyone want to finish my literature review?
Fuck no.
Technically.
There is no button for. Oh, there is no microphone here. Okay, we can see some pictures. Okay.
I've had way too much fun.
No, I think it is good
What's
temporary.
this? Picture inside of a picture inside of a picture inside of a picture inside of a picture.
It is because speed of light is finite,
Yeah.
and it takes time before photon gets to the camera.
Even though it's at the speed of the light, we had to deal with electronic speeds. Is that the purpose of fiber optics? Because fiber optics use light to transmit data, don't they?
Yeah.
Yeah. The nice thing about fiber optics is that you can like bend it and all that shit and like whatever.
Oh yeah, because we did that dumb lab. That was really a big fail.
Fiber optics lab?
In 252, yeah.
I don't remember doing that.
It's like the last one, your second to last one.
Fiber optics one is object lab. That's pretty cool.
There's like 3 of them in the fiber optics.
The last half of that physics 2 lab is basically just one big fail. I don't even think we did a lab report for like the last 3, it felt like. Where you basically said, yeah, whatever you put down was gonna, because it was like, you basically had to show us exactly how to do everything.
Right, yeah. Well, because I know that there was a couple of them near the end that we just, like, TAs just agreed not to do a lab report because, like, why?
Why? Because you knew it was not going to be well.
Well, yeah. Because I know that there's, like, the first couple where you're doing, like, the pith balls and then you're doing,
Okay,
like,
yeah,
the computer software, like that, you know, that ancient stuff. And it's just like, well, like, what are you going to write a report on, you know?
I remember that one lab where we basically sat with you for like a good hour trying to figure out what the equations were you were supposed to be like telling us.
Oh, yeah. Yeah, see, now that I'm in optics, I actually know, like, the conventions for all that. Like, I understand how that's supposed to work. But then I hadn't taken optics, so it's just like, why is this negative all of a sudden?
we're like, it was like a group of like 5 of us, or like,
Right.
all like at once trying to figure out what the hell's going on. I think at one point you realized that it's not even worth, like, we spent like so much time that you said, okay, we're just gonna skip this section and I'm just gonna talk to the TAs and ask them if we're even gonna do a lab report on this.
Yeah.
So Dimitri, I have a question. What do we do in PChem lab?
I taught it once at South Dakota, but never here. Typically, it's bomb calorimeter for like first lab.
Okay.
Yeah, you do a lot of spectroscopy.
Spectroscopy?
Yeah.
Oh.
You measure the like a CL-CL bond operations and stuff, and you characterize that.
Okay.
You do desorption spectroscopy, so what he does in his lab, you know, like surface desorption,
Yeah.
do that for a while.
I don't want the analytical tool out of me in freeze. So, as a physics major, Landon, do you have to take writing in the sciences, or did you take a different one?
I took metaphysics. I'm in it this semester, actually.
Oh, so you can take that instead of writing in the sciences?
Yeah, it's an upper level writing credit, which is nice because it's actually like interesting. I mean, it's
This is what this literature review is about. It's my writing in the sciences.
yeah. See, I've heard that class is like straight garbage.
It is, yeah.
Oh,
Like-
no, completely.
Like there, you know, yeah, like there's nothing of
Like,
substance
the
there.
next
It's
project
like
is
high
a
school.
feature article.
Ooh.
The
See.
only thing that's been helpful was when we had to write a CV and a personal statement.
Yeah. Yeah, but I mean, I don't know.
didn't even
You can
do
find
that.
stuff for that online.
See,
You know?
the
We
other
made a
class,
brochure.
so everyone else in the class basically did a resume except for like a select few of us who knew that we were going to move on to more academic stuff.
Yeah.
And
Yes.
also, I don't have much job experience except lab experience.
Yeah.
So I looked at a CV was a better pathway.
Well, yeah, if you're going academic, you definitely want to do CV. But yeah, my assignments are like describe like the presentist theory of time and the four-dimensionalist theory of time, and like, you know, which one do you think is better? Like, yeah, so like basically the four-dimensional theory of time is like time is just a fourth dimension of the three spatial dimensions that we have. So like everything, usually a four-dimensionalist would say that like everything exists eternally, right? Whereas like a presentist would say that only things that are like in this particular moment right now exist, whereas like nothing else does. But that
For some weird reason, what you just said makes way more sense than whatever we talk about in this writing in the sciences course.
But yeah, it's like, you know, like write
It's just like
write
one-
like a short response, you know, no longer than 500 words about like,
It's
you know, like
one
what these
big
things are and what
philosophy
you think
class
about
on
it.
Physics.
Yeah, basically. It's kind of nice having a physics background because then I can just shit all over the presentist view. It's just like, well, I mean, this doesn't make any sense because like there's no absolute time frame. So like, you know, even if there is one, you know, like what if we're too far
Is
away
it-
and like none
time
of that
is a
information
human
gets to us, then we
construct?
don't exist.
I mean, time is technically a human construct.
Is it though?
I don't know. I'm talking to the physicists here.
Well, thanks for electing to invest your time into this activity. So, who we are and what are we doing here? I don't know. We're just doing homework. Without much philosophy. Well, actually, if we look for big goal for our individual research projects, you do have most of the components. The code itself, you have an idea how you will design potentials. You have a separate meeting for this. Last time, for those who attended, we did observable that tracks reaction yield as function of time, and it is included in the code that I've sent right now and a week ago. And the last two components two or three components that may need to be added to the code is determine rate of transfer and discuss how to fit this rate of transfer into Arrhenius law, which can be near and dear to hearts of chemists who took kinetics in the recent past. But it's not for now. Now we are looking here. So, what is suggested to do in the homework? Did you went through? Did you read it?
No.
Go ahead. So when I was designing the homework, I didn't knew about existence of Austin. Because I admit I repeatedly offer same homeworks from year to year. But after his presentation, whatever, 2.5 weeks ago, it looks like it should be his favorite subject. So I will repeat whether it is right or wrong, but it was things declared by Austin that the width of the Gaussian wave packet in harmonic potential will grow, maybe quadratically, and uncertainty of momentum will not change. So he hypothesized that conclusions and qualitative behavior of the uncertainties of position and momentum behave the same way in free space and in the harmonic potential. Today is a time to check it. How do we formally address it? Well, we cannot be too much philosophical. We do not want to derive equations right now, to have more relaxed evening. So we will simulate it. The code allows to have the harmonic potential, which you may have done, and Austin for sure did it in the past. And you do have modules in the code that allow to track and plot and analyze uncertainties of position and momentum. For our interest into these uncertainties, we shouldn't care much about expectation of position and momentum. But if you do not want to garbage our brain and flood our screen, we may want to set up initial position of this Gaussian wave packet near the equilibrium, and we may set up initial momentum 0, so that in analogy to classical mechanics there will be no motion. And then check what will happen to the uncertainties of position and momentum. This experiment was done by another attendee of this meeting, by Braden, even before we started practicing this wave packet propagation code. He did it for free space with an analytical solution when he did an introduction of how to make movies in MATLAB. So wave packet was staying still, and its shape was expanding. We are going to do the same, so no best initial position, optimal near equilibrium, no momentum, and tracking only width, which is uncertainty of position, and uncertainty of momentum. The questions in the homework are formulated mostly towards the uncertainty of position, but we may go a little bit further and work on momentum too. I'll skip this boring stuff of making connection with ground state of oscillator width, but it will be really helpful when you wrap up whatever the data that we generate and prepare them for submission. So what all these series steps just suggest a little numerical experiment. Select fixed curvature and play with different initial values of uncertainty, which is variable x var, I think, and see what happens. And then you will be able to answer questions and feel it out. So how do we? But you don't need help to make this harmonic potential, right? You just write x dot squared, and you offset it by equilibrium position, and you multiply it by thing that today in class we found as h bar omega divided by 4. for curvature. A parameter of the curvature. Okay. So please open the code and try to run it. So on this station it will be a little slow, but I will walk around and see how you are running it. Because on your terminals it will be much quicker. So what do you see? Oh, okay. Goes back and forth. It's a really good choice that you have it on your personal computer. It makes you independent and you can do this at your home place. So what?
At some point, the red
Huh?
wave overtake the green wave. I don't know. It's like when it starts oscillating back to the left, the red starts peaking before the green. I don't know what that.
Well, ask Braden.
Error accumulation.
Huh?
Error accumulation.
Oh, duh.
And how to how to reduce the error.
Decrease time step in spatial discretization.
Okay.
So we see here it's still going on, and it is a real challenge to human patience to wait until it is done. And on this terminal it is a little longer because it also processes the video signal. On your terminals, you're probably 10 times quicker. So, but in order to minimize, and if you would do serious science, we would compile and submit it in parallelized form on the supercomputer over multiple cores. But what did you observe? What is your observation?
The way again bounces up and down when it doesn't.
So the center of wave packet bounces forth and back, right? But what about the uncertainty?
It also oscillates.
Yes, basically that's it. So tell it to Austin.
The uncertainty oscillates.
So and what does it do on the first time at the beginning and the short time after we have launched it? So here we have this sigma sub x. Does it grow or decrease? So in free space it was growing, here it is decreasing. Are we on a threshold of a big discovery? Will it decrease all the time? is there a chance for it to grow? What is your natural intuitive thinking?
Maybe it was later on in that oscillation.
Yeah, if you select the initial time point somewhere here, then it will grow quadratically for in the time vicinity of this point. So you may want to make an numerical experiment. Select the x variable of, let's say, 2, 3, and rerun this stuff once again and see what will change. But before you do it, another piece of thoughts. Here is oscillation of the average position, right? Can you come and help? Please.
Yeah.
Otherwise, it's boring for me to explain everything. So, can you point the period? Just a moment. It's nothing.
I mean, if I remember from my math knowledge, which has been a while, isn't the period just from here to where it comes
Yeah.
back to the same point?
So, approximately how many time units? It's probably atomic time units.
140.
140. Okay. So it takes.
We could just
one-
make it almost
one-
150.
huh?
We could almost make it. It's,
It takes 140 for the full cycle of oscillation going forth and back.
mm-hmm.
Now let's look on the
Uncertainty
uncertainty.
factor.
What is the period of full oscillation of uncertainty?
75-ish.
How does it relate to period of the?
Almost half.
It is exactly half. Well, we can prove it mathematically, but yes,
Okay.
the observation is almost. Yeah, thank you much.
Yeah.
So now you guys did a discovery. Oh, Austin continues making hypothetical statements and discovers about oscillator. The uncertainty for Gaussian wave packet placed in harmonic oscillator doesn't grow or drop. It oscillates, and it oscillates with twice shorter period or twice higher frequency than nature of frequency of oscillator, than frequency of position oscillations, right? Good. Okay, let's do the next experiment. Just put in the small value of x var, of initial uncertainty. And if I do want to accumulate many movies, I can call it just add index. Add index here. Save and so it was 40. Now I put, let's say, 4. Save and run. Even without waiting to this thing to complete, what do you observe? How does the uncertainty changes?
The uncertainty is lower near the middle now, and it expands as it gets out towards
Yep.
the greater potential.
Mm-hmm.
Whereas the other way, it was going vice versa, where it would narrow up near the edges and then widen up in the middle.
Mm-hmm. But then it consolidates back.
Mm.
So depending on the initial value of the uncertainty, we just place it at a different phase of the oscillation. We start at the maximum or minimum, but it probably oscillates around some central value. Maybe, well, if you were not listening, now it is time to listen. I'm going to say something that I believe is valuable. Or if you are watching it on the recording, start listening. Second, minute number 24. So we may set up a hypothesis that uncertainty oscillates around its best value. So if you put it too much, it starts going down and oscillate. If you put it too small, it goes up and oscillates. But maybe if we guess a very correct value of uncertainty, it will not oscillate at all. Or if we deviate our initial value of uncertainty not very far, then it will oscillate with much smaller amplitude. So let's set up it as a hypothesis and then just try to guess what is first, if this hypothesis is correct, and if it is correct, then we may want to find this optimal value of uncertainty just by plugging in different initial value of x var and seeing what happens. I'm done with potentially smart saying. You can stop listening now. So has the same amplitude of oscillations, it just starts at different point. So our best value of uncertainty is expected to be between 4 and 40. You can just take a midpoint, something like 20, and see what happens. Does it take a little longer? If you become impatient, you can change the variable tau at the beginning, but then you will accumulate much more errors, and
Yeah.
the wave packets will not be smooth somewhere, but they will start wiggling.
Oh, I had it at one point, the X bar, and I saw that wiggling. So
So, quick question. When you say that it wouldn't oscillate or anything, would we be looking for just like a constant Gaussian wave then? Or just going back and forth?
Yes, it is expectation. So we didn't prove it, but I have a feeling and previous experience that it will be the case.
Yeah.
So it will be shape that is not changing, but just translating force and back. But now we need to guess experimentally, and later in the class we can find it, or during your homework completion, you can just find it theoretically from class material. What is the theoretical value for this optimal uncertainty?
Pretty close.
Okay, so what is your value?
I'm at 11 right now.
I'm at 10.
I just did 10. It was.
Not
seeing if
London is
better.
closer. London is
Yeah.
closer.
Yeah. That's great.
Make your stats, man.
you could tell it's almost the end of the week.
Yeah. Short week even. Gonna fuck around all day Friday.
I wonder if it's 11.5.
It might be. Well, I'm guessing it's probably somewhere in the middle of like where it's oscillating around, right? Like if you find that midpoint, then it should just
Yeah,
stay flat,
you could probably do the calculation, but that's not fun.
right?
So this is thing that we were discussing. I'm just bringing it to the bigger screen. Now we start at different phase, but it still oscillates with double frequency. So it starts with minimum, go to maximum, and oscillates with double frequency. Now we are trying to check if it really oscillates around some midpoint between 4 and 40, or maybe some other values, and see what this value is. if you were not here last time and you're curious what are these ugly step functions, those are pre-made things for reaction yield. They're already added there, and it is 1 if wave packet is more on the left, and 0 if it is, and it changes when it goes from left to right. Right now it is no sense, but if it will be passing through a barrier, it will be very appropriate. Just do not have time to make 1,000 codes for each situation. So you're telling 11, right? It's save. Why doesn't? Oh, it moves just to entertain us. But why don't I should stop it and for this exploration we do not need any initial momentum, just to have a clear experiment. So I'm putting p not equals 0 to make it. It will be less motion, but it will distract us less from analysis.
Smaller than 11.3?
Yeah. So I'm doing 11.2 right now. 11.25.
I think it's greater than 11.2.
Probably. I don't know. I'm about to find out. You do 11.1.
I just did 11.1.
Well, you kind of chill.
Okay, I just wasn't working myself. I was listening around what you guys are telling, and Vanden told 11, and I just put it in the middle. So maybe if someone has a very good eye, we will see that it expands a little bit, but it is not. One probably needs to zoom in to observe it. Zoom in, zoom in.
My old man eyes can't take it.
It's still hard. It almost looks like a still picture, but if you wait long enough until it is done, we will look on the oscillation profile, if any, and see what happens.
Are you okay?
Funny, bro. It's only funny for other people.
Looks like it's just shy of
What's your
11.2.
What?
Just shy of 11.2. Just a good bit.
Yeah, I tried 13. It's still pretty fast. Maybe 12, maybe 11. Does it have to be an integer or?
No, it's not. At least in
Could it be like a 1.5 or something like that?
yeah. I want one more iteration. No. Well, I will not keep the intrigue.
10.5 right now.
Huh?
10.5 looks pretty good.
Nah, man.
It's greater.
It's way bigger than 10.5.
Way bigger?
Not way bigger.
It's like 11.
I'm testing 11.15 right now. I'm getting pretty freaking precise.
It is closer, yeah. Is it done? No, it's still.
No, it's still running. You just can't tell.
Yeah, probably we can do a little programming effort and make a time value being changed somewhere, so that one can identify whether it is actual movie with not much motion or it is a frozen screen.
It's like it's just a little bit higher than 11.15.
You're getting way too junior about this.
This is his mathematician side from
Right.
It's gonna happen like down to like the 10,000th.
I'm down to the third decimal point. Or the third decimal place after the
One of my friends, I will tell, it is not joke, but it's a little limited fun about education. No one here, no one who is present in the room in the education program?
No.
That would have been
I'm gonna
Beth and
be.
Ian.
Huh?
That's Beth and Ian.
Oh yeah.
Beth and Ian.
Yeah.
So there is an assignment for middle school kids at the beginning of math. Experimental determination of the pi value. By taking a piece of material, cutting it square, weighting it on the scales, then cutting a circle, weighting on the scales, and compare these two numbers. So we are doing kind of similar things. So we are determining experimental an answer that can be figured out just from shape of the ground state of the oscillator. But hopefully we are having fun.
Real freaking points right now.
I think Landon is.
Which major or minor are you using right now?
Math and computer science.
How often does it change?
What's that?
Major and minor.
Oh,
Doesn't
they don't
change
change.
yet.
It's just
No. In your you probably have power to change it by your free will from time to time.
Yeah, I suppose. I don't know.
So how often do you change it?
I guess I don't really think about it that much.
Okay.
I mean, I suppose like several times a day, because my class schedule is basically I have like one physics class, one computer science, one chemistry, one math, and right now I got one philosophy, and next semester it's going to be industrial engineering.
I see. Broad.
Yes.
Just add Chinese in while you're at it.
Yeah, right. I might as well.
So when we started 11, it goes to 11.3. So I would try something like 11.15.
That's too much.
Too much? Less? 11.1?
Or wait, no, sorry, no. 11.15 is not quite enough. I'm at 11.8 right now because 11.175 wasn't quite enough.
But midpoint between 11 and 11.3 would be a good guess. But
Yeah.
you see that we are narrowing down the value, and even now, for naked eye, it looks like it just stays and does nothing.
Put it in. Now you're gonna have it, aren't you?
Oh, I'm zooming in now so that I can actually see the oscillations. Oh, I'm just a little bit shy still. Just a little bit. You know. It's probably like 11.181.
So 15 is too much?
Yeah.
Your experience?
So 11.18 is just barely short. So I'm trying 11.181.
Okay, I'll try something simple. It's too complicated. Save and run.
Would that be engineering at this point, since I'm getting out to like X amount of decimal places?
You don't care about the analytic solution. to this
Right,
problem.
I'm
You're
just trying to get the
experimentally
numerical solution,
testing it.
yeah.
So yeah, definitely engineering.
I just need to know beyond a certain,
You don't need to know why, you just need to know it.
yeah.
But what does this picture remind you? What does it look like? Does it look similar to something that we went over in the class?
Like a
there was a-
double, well, I
Huh?
don't know.
There is a potential surface, quadratic, harmonic. And does it remind any of the eigenstates? No?
Oh, it's got to be the ground state.
Yes, yes. Now it is discovery of London.
The potential?
No, the function.
Oh, yeah.
And again, let's look philosophically. I'm going to say something that is potentially valuable, maybe. So if you're watching the recordings, please listen. Try to listen. So philosophically, the eigenstate is such state that doesn't change in time, that is not affected by Hamiltonian or evolution operator. Here we have a wave function. Well, we are plotting wave function squared, but it should be similar. We are acting by evolution operator, and it doesn't change in time, which means most likely it is an eigenstate. And it goes along with your hypothesis that most likely it is a ground eigenstate, right? So the interesting continuation of this hypothesis that the optimal width of Gaussian wave packet is expected to be the same as the width of the ground state uncertainty. I'm done with telling potentially valuable things. Stop listening if you're busy. Due to inactivity, the system will shut down.
What?
No, return to complete control page. Inactivity? We were super active. So I bet it's still running, but for a long period of time, nothing is changing. So it's very close to the eigenstate. Actually, it was not planned, but maybe if we apply, if we program creation operator, apply it to here, it will convert it to this a camel with two humps that will also stay intact in time. So if you have nothing else to do, you can try it. But before going to this, we are going to record what is our value. Then either here or at home we'll calculate by pen and paper width of the ground state for this potential, which will be like h bar over m omega, right? Okay, 115 is a little insufficient, so 1.18 or 1.17 could be the right value.
18 is too high.
I'm down to like 5 decimal places right now.
That's impressive. Damn it. Oh, now I have a grading criteria, number of decimal places.
Yeah.
Oh.
Okay. Did you got an idea on this? How can you summarize it?
Solve for the width, plug it in.
Huh?
Solve for the width, plug it in.
No, philosophical summary.
Oh.
Christian?
No, I was just checking, sorry.
Can you summarize what we discovered together? Like,
Well.
how does uncertainty of Gaussian wave packet in harmonic potential behaves? Are there some trends to observe?
Other than the decrease in X bar increases uncertainty a little bit, or its speed is sped up uncertainty.
Well, it oscillates
Yeah. Oh, okay. Yeah.
around some central value, around some optimal value. Uncertainty. If uncertainty is too high, it goes down. If it is too small, it goes up.
Yeah.
But if you select something in between,
Oh, then it stops.
yes. So
Yeah.
what is this? What is our hypothesis? What is this optimal uncertainty?
11 point. 18034.
Perfect. But what is this uncertainty if you, in philosophical sense, we can, by one button, we can change the steepness of the potential. Not the numerical value, but the idea behind it. You do. We were discussing it. Huh? Yes. Uncertainty of ground eigenstate.
Okay.
So if you create Gaussian with uncertainty equal to uncertainty of ground eigenstate, it will not change the shape. So if we go back into and add the momentum, non-zero momentum, so it was another hypothesis by Austin that it will be the same shape, but it will translate from left to right without any change. So we can just cut a piece of paper and move it left and right. Does it match your expectation?
I think so. Didn't I say it was constant?
You told that one may expect constant shape to just offset to shift left and right. It's still moving. It approaches to the turning point, stops, and then accelerates in the opposite way. So the Dr. Glauber was a candidate for a Nobel Prize. He didn't got it, but this discovery was considered to be awarded with Nobel Prize. So there is a class of states that do have uncertainty equal to the uncertainty of ground state, and they may move with expectation value of position and momentum, but their uncertainty stays constant. And they are referred to as coherent states. So I have solid plans to cover it in the class, but now you have a favor to start thinking of it a little ahead of time. Okay, what else can we benefit from this little code with this initial values? Remember that 2.5 weeks ago, Austin made another brave statement, hypothesis that uncertainty of momentum of a Gaussian wave packet will behave same way as in the free space, so will not change. So it's time for us to plot uncertainty of momentum and check whether it is constant or doing something else. Do you stay under this hypothesis, or you may develop a new one?
I don't entirely remember it, so.
Oh, okay. What would we expect for uncertainty of momentum? We know that general uncertainty relations, the product of uncertainty of position and momentum, is either constant or growing.
It's probably going to oscillate exactly out of phase with the position.
Mm-hmm. Do you like the idea of fun? So when position is most certain, the momentum is most uncertain. But maybe we can make another statement, that hypothetical statement. If we select the best optimal uncertainty of position, maybe the uncertainty of momentum will not change as well. So if we set up too high or too low uncertainty of position, then uncertainty of momentum may oscillate as well. But if we look at this optimal uncertainty of position, maybe momentum uncertainty will not change. So how do we check this hypothesis. We don't want to spend too much time. We recall that there were variables related to uncertainty of momentum, A, V, S, P. And if you forget, we can scroll through the code and so it looks something not much, not very agreeing with our hypothesis. So you cannot tell that it is oscillates, and you cannot tell that it behaves constantly. So probably we can go back to oscillating uncertainty and then re-inspect this once again. So if you look on the last line of the code, it has presented template to inspect for this momentum uncertainty. The real part is needed because most of variables by one method it does oscillate. It's better. Okay, now two methods coincide, but they show something that doesn't match any of our hypothetical expectations. I put it, I pressed this percentage down so that you don't forget the value.
I'm starting to see oscillations.
I run it once again and then I extract
I think I'm done after this one.
the variance.
I think I found it. So I got down to quite a few decimal places.
That's impressive.
Sorry.
Yep. Just remove the percent. Maybe
Oh, fuck. It's starting to get a little wonky in there.
You're a little wonky.
I know.
How about numerical error?
I mean, it's not looking like an oscillation anymore. It's kind of just doing its own thing. Yeah, so I'd probably call that numerical
So
error.
hypothetically, you can't actually reach a point of absolutely no oscillation, but
Well, I mean,
practice, is that possible?
it's not like a periodic oscillation anymore. It's kind of just a wonky thing. So I think I pretty much found the limit.
Oh, okay. I was like,
Until you
so,
reduce your
so
times.
in practice, it's not possible to completely stop it.
No, probably not. I mean, well, like, I don't know, it's starting to get kind of disfigured.
Is it increasing as it goes over time?
I guess, yeah.
Make your P not zero or
well, it doesn't matter. It's just if you're bored to see non-changing shape, you can keep it. Instead of setting P not zero, you can do move your
Right.
head.
Here
And you
we go.
reduce the effect. Change the. Yes.
Oh no.
So it was stretching rather than attracting attention.
Yeah. No, my shoulders are just not liking the cold weather right now. Never said I was a young person. I feel like that my bones landed. Bad weather is coming.
Yeah, it's getting a little wonky. I think I'm at about the numerical limit here.
So how do you interpret this? Fix.
I was thinking about it, then got distracted.
I wonder why.
Yep. That's the ticket right there.
Chicken, chicken.
Mm-hmm.
Are you plotting the same as me, or did you change it? All I did was uncomment.
Let me check what I'm plotting. Yes. So by some reason the outcomes of two methods are quite different.
That like.
But do you have an even if you do not have a complete answer to this puzzle, do you have any hypothetical vision of what is going on?
Oh, it was a big dumb. It looked like a ball bouncing.
Yes, well, everything we do is
It was just that sort of picture did at that moment.
so here is uncertainty of position, and here is our last figure with uncertainty of momentum. And we do not have coincidence between methods, and their disagreement is substantial. It makes a little worries. But quantitatively, at least I think that I'm doing this experiment for the first time, so I cannot guide you too much. We are thinking together. What when the uncertainty of position increases, the uncertainty of momentum decreases. So it was a hypothesis of London. So they act in opposite phase.
So if we increase position,
Uncertainty.
the momentum will decrease.
Uncertainty.
Oh, not
It's not. If you would take this wave packet and convert it into momentum space, it will be Gaussian, but it will become broader or narrower either in this space. So it is a little too abstract. So here, at least intuitively, we can understand what is going on. But a strange thing happens if we approaching the optimal, almost constant uncertainty of the position. Then uncertainty of momentum, instead of moving in the oscillatory way, it stays most of the time zero, and then it makes spikes. So mathematically, it looks like the function has division by zero, or very close to division by zero. It's good food for thought for the future. I don't know how much of the images were recorded. So maybe it was on the screen that was recorded.
This is slowly.
Line up. Yes.
Totally make a music video out of that.
You know what's missing? It's like that really dumb cat picture that guy took. Lasers in the background.
You
Look,
can
the
come.
cat
You can
catching
come
up.
and play it. I'm not sure that if I will place it on YouTube, maybe it will get much more hits than any of the scientific content. So, I'm not sure if you have Steam for anything else. Do you have open questions to discuss? Save screenshots or send email to yourself with this information, as it will be very helpful for completing homework reports. This information is more than needed. And then in the remaining labs, we will tailor our efforts between. Does the figure open mouths also in this harmonic way? No, I do not want it.
How the further back it goes, the less like color definition it gets.
Right.
So, for the coding part of the project, the potentials is not my headache. It will be headache of participants. So you design potential, but what I will provide the couple of additions to the code that make convert the data into rate of transfer, and then we will discuss how to make Arrhenius plot. And then we should have 1 or 2 meetings when everyone will just come and practice their own research project with a mode of me circling around the audience and trying to help if possible. If time allows, I have another code to share about nuclear magnetic resonance, which could be cool, but we need to observe available duration of the semester.
So what exactly does the NMR code show?
Free induction decay and spin echo.
Of what kind of system?
Right now, I can share code for doublets, but it can be easily expanded to triplets, quartets. It is not commercial code. It is something simple that you can write yourself. So it's not a package. It's a little MATLAB script. More questions? Okay, meeting is over. I'm going off this funny record.